Press record. All right, so today we'll have Nat giving the second lecture.
Okay, thanks for being here for lecture two. So this is the second lecture on representation rings. The third lecture, fourth lecture, and fifth lecture are all independent from this material and from each other. So you should feel free to drop in anytime you want, but these first two lectures fit together. We concluded last time by talking about character theory after discussing representation rings, restrictions, and transfer maps, and doing some examples. We talked about character theory, which is one of the best ways that we have to get a hold of the representation ring of a group through this character map that's right here. That is a ring map. Where's my weird? Which is right here, which is a ring map from the representation ring of G into class functions on G, taking values in Q adjoin all roots of unity. Um, there's one piece of notation that I wanted to add from last time because I'm going to need it today, and that's the notation for this Kunith isomorphism. So this Kunith isomorphism is this map from Ru of G1 tensor Ru of G2 to Ru of G1 times G2. This is a ring map, and it's an isomorphism in this case, but it has a name in algebraic topology, which is the external tensor product. So this is denoted with a box times. So we got a G1 representation, a G2 representation, and I tensor them together to form a G1 times G2 representation. Okay. So that's box times. So for lecture two, I want to continue where I left off, and I want to talk about some examples of character maps. And so we're going to do two examples. So one is going to build on the work that we did already. So so this is an example. If G is a cyclic group of order n, then I've got this character map, and this goes from Ru of Cn to class functions on Cn, taking values in Q adjoin mu infinity. Of course, the conjugacy classes in Cn all have exactly one element in them because Cn is abelian. And the element, we gave a presentation for Ru of Cn last time, and we had this special element x, which corresponded to the action of Cn on the complex numbers given by multiplication by e to the 2 pi I over n. And that tells us, since we know what that does, it tells us how to compute this character map on this, because the trace in this case is just reading off the way that the element acts, or yeah, the way that the element acts, or the way that the action works. And so x goes to 1 mu n squared up to mu n to the n minus 1. And that determines this ring map because Ru of Cn is z adjoin x mod x to the n minus 1. And mu n here is a primitive nth root of unity. So we learn from this that Q adjoin mu infinity tensor Ru of Cn is just a product over the elements of Cn of Q adjoin mu infinity. So this is what I was saying about after this base change to Q adjoin mu infinity, the representation ring is just a product. And in terms of the multiplicative group scheme, so this is not important for the purposes of this talk, but it is useful to think about things this way. We pointed out last time that Ru of Cn is the n torsion in GM. And what this is saying is that if I base change the n torsion in GM to Q adjoin mu infinity, I get the constant group scheme, which is the cyclic group of order n over Q adjoin mu infinity. Um, and again, it's not important that you understand what that means, but if you do have some idea of what that means, this is the property. This is basically a defining property of Q adjoin mu infinity. It's the thing that tells us that Q adjoin mu infinity is the right coefficients to take for the character map. Okay, so that's example one, cyclic groups. And then the other most important class of groups that exists, or maybe the most important, is symmetric groups. So that's our important example. This is G is sigma M, a symmetric group. And in this case, our character map chi goes from Ru sigma M to class functions on sigma M, taking values in Q adjoin mu infinity. And as we pointed out previously, it really lands in the z hat times invariance in there. And we want to say something about this map. So let's think this one through for a little bit. So if I have a conjugacy class sigma in sigma M mod conj, we know that that's determined by the lengths of the cycles in the cycle decomposition. Um, and uh, and we have this action of z hat times on sigma M mod conj. And this is the thing you really want to understand in this example because it's surprisingly degenerate. So if I have some L in z hat times, and I have some conjugacy class um, here, then the way L acts, well, I move L into z mod, say, the order of sigma times. So this maps to here. And then what I do to sigma, the action of L on sigma just sends it to the conjugacy class of sigma to the L. Um, but if L is in Z mod the order of sigma times, well, the order of sigma is the LCM of the lengths of the cycles. And so that tells us that L really represents a unit in Z mod the order of each of the cycles. And so if I raise some cycle to a unit there, then I get a cycle of the same I get a cycle of the same size, or I get another whole cycle. So so this implies that sigma to the L has the same cycle decomposition. Cycle decomposition as sigma. The lengths of the cycles are the same. And that implies that the action of z hat times is trivial on sigma and mod conj. So since z hat times is the Galois group of Q adjoin mu infinity over Q, we learn that that the character map actually lands just in, since the z hat times action on sigma m on conjugacy classes and sigma m is trivial, the character map lands in rational valued class functions on sigma m. So Ru of sigma m lands in CL sigma m Q. We just end up taking invariance of the target, which is Q adjoin mu infinity. And well, we took the invariance for the whole Galois group. But when we define the character map, the way it was defined was by adding up some roots of unity along the diagonal of a matrix. And that process always has to land in the algebraic integers because we're just adding up some roots of unity. And so, in fact, inside of here, I've got the integer value class functions. And since we must land in the algebraic integers, this map must factor through here. So we can conclude a kind of amazing fact about characters of representations of the symmetric group. They're just always integer valued. So the character of a virtual representation of the symmetric group is some integer valued function on conjugacy classes in the symmetric group. Okay, so those are the two examples that I wanted to talk about. And next, I would like to jump into the relationship between these character maps and restrictions and transfers. So let's start with restriction. This one's pretty easy. So if I have some map phi from H to G between two groups, well, we get an induced map, which I'll call phi mod conj, from H mod conj to G mod conj. And I can just take functions on this map to get a map the other direction. So this induces a map from CLG Q adjoin infinity to CLH Q adjoin mu infinity. And it turns out that this is the map compatible with the restriction map on representation rings through the character map. So let me just summarize this by saying there's a commutative square. Can you hear him? He is barking. Can you hear him? Does it come through? It doesn't come through? That's amazing. You can, this gives us a commutative square, in this case of rings, um, RU of G, RU of H, coming down, CLG Q adjoin mu infinity, and then over to CLH Q adjoin mu infinity. So here I've got restriction along phi, and here I've got this just restriction on the level of functions along phi mod conj. And this is a commutative square. Riff, quiet, quiet. Riff. Must be a dog out there. Okay. Uh, um, the transfer is a little bit complicated looking. So wait, I'm gonna go shut the window. Give me a second. This is too much. What is that? Sorry, dog was barking in my ear. Uh, so I want to do the same thing for the transfer. Let's figure out what the formula for the transfer is on the level of class functions. So let's assume that H is a subgroup of G. And I want to give you what we want is a formula for like transfer HG from CLH, Q adjoin mu infinity to CLG, Q adjoin mu infinity. And I'm just going to tell you the formula first, because when you first see this, it feels like it kind of comes out of the blue. So the formula for this on a class function f, so here's some class function f on h. So I'm going to apply the transfer to it, and I'm going to evaluate it on a conjugacy class in G. So I'm going to give you two formulas. So the first is it's 1 over the order of h times the sum over L and G, such that if I conjugate G by L, it lands in H of the value of F on the conjugate. And said another way, there's actually lots of ways of giving formulas for this, but they're all equivalent. This is the sum over the cosets of H and G with the property that LG L inverse is in H. of F on LGL inverse. And both of these are actually quite useful. The second one is worth saying because it makes it clear that this formula doesn't care what the um, what the coefficients for our class functions are. I could put any commutative ring there, and there's a perfectly good transfer formula. So it doesn't need to be rational even. Uh, and But the first one looks like there's a division. The first one is actually often a little bit easier to work with when you're explicitly calculating. So that's why I think that one's worth saying. And you might say, okay, yeah, but where does this come from? There's actually a really nice answer to that question. When we consider the character map, so this is from like RU of G to class functions, the map from RU of G onto one of the factors is a kind of restriction. It's kind of like restricting to a cyclic subgroup of G and then using that to map into Q adjoin mu infinity. And so the reason there's a sum here is because you're doing when you apply the transfer on representation rings and then do the character map, it's like doing a transfer and then a restriction for which the double coset formula applies. And so this formula right here is actually a form of the double coset formula that's been specialized to the situation of doing a transfer and then a restriction and then including into the coefficients of your class functions. So that's the real reason why this is the formula. But this was only for an injection, and I want to also tell you what the formula is for a surjection. So if I have some surjection phi from H to G, then the formula here uh, is given by 1 over the order of the kernel of phi of the sum over H in phi inverse of little g of f of h. Um, and I'm not summing over the size of the conjugacy classes in phi inverse of square brackets g. I'm really summing over all of the elements in the fiber over little g. And I think I'm not going to give a lot of intuition for where this one comes from. There's a sense in which you can think about it as having something to do with Burnside's orbit lemma, orbit counting lemma. But maybe that's all that I'm going to say about that. Maybe until the next lecture. Okay, so that's all that I wanted to say about the relationship between the character map and restrictions and transfers. I didn't do an example there, but I want to jump into the power operation stuff. Are there any questions at this point? Oh, one important thing to note about this last transfer where we're transferring along a surjection, I can't get rid of the quotient in this case. So this is a formula that does not make sense unless I'm working rationally. That's an important observation.
Probably I have a question about the representation ring should have the laminar ring structure.
Yeah,
You mentioned it had for this class function, it also has the laminar ring structure,
yeah,
right?
yeah. But
You will mention later or
well, I will get to wherever I get to. I'm not exactly sure where I'm going to get to. So we'll see.
oh okay, fine. Thanks.
Okay. So let's talk about power operations. So the idea behind power operations is very simple, but somehow it leads to a lot of complicated stuff. So the idea is to take some G representation V, and all I'm going to do is raise it to the nth tensor power, which is something that I can do. That tensor product is over the complex numbers. And when I do that, since it was a G representation, well, there's an action of G to the M on this, which is like a coordinate-wise action on the simple tensors. But there's also an action of the symmetric group on this. That's terrible. That's also terrible. Given by permuting the tensor factors. And these fit together to give an action of the semi-direct product of G to the M and sigma M on this thing. And we have a special name for this semi-direct product. This is the Reith product of G with sigma M. Uh, and uh, if you haven't messed around with Reith products before, well, I suggest pulling up the Wikipedia page and just seeing how multiplications work. It's fun, but the way the multiplications work are like multiplications in a semi-direct product because it is a semi-direct product. Okay, maybe that's not that useful. So we're going to define the nth power operation on the isomorphism class of V as a G representation to be this thing. And this is an RU of G Reith sigma M. And I haven't told you how to define this on virtual representations yet. It is not obvious. We'll get there and say something about it in just a moment. But I want to note a few first properties of this thing. So the first is multiplicativity. So it is the case that if I have two vector spaces or G representations and I take this is the same as V tensor M, tensor W, tensor M. And so this implies that PM is multiplicative. But since we're raising things to powers, you really should not expect things to be additive. So let's have a discussion about additivity. I'll write additivity fails, so it's clear that we don't mean to show that it's additive. So as vector spaces, well, I can take the sum of two vector spaces and raise this to the nth tensor power, and then a kind of binomial formula happens, right? This is the same as the direct sum over I plus j equals m of m choose I copies of v tensor I plus tensor w tensor j. But that's just on the level of vector spaces. We want to track the actions. The symmetric group action is the most important. And it turns out that the failure of additivity of these power operations is controlled by the transfer maps. And the formula is the following. So PM of V plus W is, well, first there's a PM of V, and then there's a sum over I plus j equals m with I and j greater than 0 of the transfer from G Reith sigma I times G Reith sigma j to G Reith sigma m of Pi of V box times Pj of W, and then one final term plus Pm of W. And I could have written this all as one big sum without having the I and j greater than 0, but it is useful for future observations to write it this way. So this transfer Okay, so there's a bunch of stuff going on here. So I started with G representations, V and W. So Pi of V is a G wreath sigma I representation. Pj of W is a G wreath sigma J representation. I external tensor product those together, which means going through that Kunath map. So that gives us a G wreath sigma I times G wreath sigma J representation. And then I transfer along the inclusion of G wreath sigma I times G wreath sigma J into G wreath sigma M. So that's what's going on in the middle. And you might wonder why this is the case. Uh, it says that these transfer maps are somehow playing the role of binomial coefficients, and that's really true. That is what they're doing. The idea is not actually that hard. Let me just state it in the case G is trivial so that we can see what's going on. So the point is that if I have a set of size M, which I'm just going to write M underline right now, and I've written it as the disjoint union of a set of size I with a set of size J, then what I can do is consider the inclusion of V tensor I, tensor W, tensor J into the direct sum over all subsets of M of order I of V tensor X, tensor W, tensor the complement of X. And this thing on the right is a sigma M representation. And I know how sigma M acts because I know how to move subsets of M around um, uh, with the sigma M action. On the left, I just have a sigma I times sigma J representation, but it's including into the summand that's exactly itself. So this map that's here is a map of sigma I times sigma J representations. So this is a sigma I times sigma J equivariant map. And since it's a sigma I times sigma J equivariant map, and the right-hand side is a sigma M representation, I can just extend on the left to sigma M by base changing here. I can just do that on the left-hand side. I'm using the transfer restriction adjunction. And when I do this, I get something that's the correct size on the left-hand side, and I can check that it's an isomorphism. And what have I done? I've taken the ith power operation, tensor the jth power operation on the left-hand side, and I've transferred it up to sigma m. So this is the idea for why that's the formula for PM of V plus W. Does that make sense? All right. Is this a question to me or to everybody? Right. We will talk about these things. Yes. Are there nice situations with which the power operations do become additive? Yes. Yes, there are nice situations. But I want to say a little bit about the move from G representations to virtual representations. So from G reps to virtual G reps, because you'd like your source to be all of RU of G. And this actually isn't that hard to do, but it is awkward to give formulas for. So the first observations are, well, what's P0 doing? P0 is tensoring to the 0th power, so it's dumb. So P0 of V, oh, I have 0 written here. I think I mean 1 is 1. So P0 of minus V should also be 1. P1 of V is tensoring to the first power. So this should be V, and that should extend. So that P1 is the identity map. And now the idea is to use induction. It's useful to have one piece of notation here. I'm going to let tr I sub j just always be tr g reth sigma I times g reth sigma j, landing in g reth sigma I plus j. Because, yeah, the right-hand thing takes forever to write. And then what we do is we use induction to define PM on RU of G, all of RU of G. And let me just show you how that process works. So for example, if I want to know what P2 is on minus V, what I'll do is consider P2 on V plus minus V, which V plus minus V is 0, so the second tensor power of that should be 0. But now we try to use our binomial expansion. So what we get when we try to do that is that we get P2 of V plus TR11 of V box times minus V plus P2 of minus V. But this minus sign that's here, which you might be concerned about, well, everything's linear. So this actually pulls out of the box times and out of the transfer. And so that's kind of the thing that saves the day. And now just rewriting what's here, we learn that P2 of minus V is TR11 of V box times V minus P2 of V by just moving things around using the 0 that's there. So that's the idea of how the inductive process occurs that extends this to all of RU of G. You can imagine that writing down a general formula for it is not the most pleasant thing in the world. But let's do one example of a power operation because I haven't done an example for a bit. So I could do the case that G is trivial. So this is a map from Z to RU of sigma 2. RU of sigma 2 has the nice feature that we have that it's cyclic. So this is Z adjoint X mod X squared minus 1. I'm going to tell you what the formula is, and you should have fun trying to figure out why this is the case yourself if you've never done this before. The formula is that an integer k goes to k squared plus k divided by 2 plus k squared minus k divided by 2 times x.
How is this mapping defined?
Which one?
P2 from Z to RU sigma 2.
Z is RU of E. So it's the second power operation. Does that make sense?
Okay, yeah, I think that makes sense.
So I just want to talk about some basic properties of these power operations. So one is special values. So like P0 of anything is 1. So P0 is the constant function 1. P1 of anything is itself. So P1 is the identity. The second property is this property that we described about the value of PM on X plus Y. So this is some big sum. I'm not going to write the whole darn thing out again. And the third property is that if I take PM and I restrict it along the inclusion of G Reth sigma I times G Reth sigma J into G Reth sigma M, where M is I plus J, what I get is PI box times PJ. So PM, I can kind of recover these smaller power operations from the bigger ones in this way. Okay. These are important because we're going to see other examples of power operations in future lectures, and these are the same kinds of properties that are going to hold there too. But this additivity property suggests the following. So failure of additivity suggests defining an ideal I sub m contained in Ru of G Reth sigma m, which is, let me write this. Let I sub m contained in here be the image of the direct sum over I plus j equals m with I and j greater than 0 of the transfer. So that transfer map goes from G Reth sigma I to the Ru of G Reth sigma I times G Reth sigma j to Ru of G Reth sigma m. We've already discussed that Frobenius reciprocity implies that that's a map of Ru of G Reth sigma m modules. And so this image is an ideal. And this is the ideal that controls additivity. This controls additivity.
Can you
Right?
repeat what you said about the implication from Frobenius reciprocity?
Frobenius reciprocity is the thing that implies that I sub m is an ideal.
Okay.
All right, an ideal B. And you see that it controls additivity by just looking at the formula, which the formula for PM on a sum, right? Like if I mod out by that ideal, all of these terms vanish. And so I'm left with these two. And so after modding out by that ideal, PM is additive. So we could call this PM mod IM. This is a map from Ru of G to Ru of G Reth sigma m mod IM. This is additive. People call this the total additive power operation or something like that. Okay. So the next thing that I want to do is talk about the relationship between the power operation and the character map. Okay? So like now we've got a fourth thing in the mix. We had restrictions, transfers, character maps. Now there's power operations, and we want to know how it all fits together. We want to know how it all fits together. So interaction with character map. And for this, I need a new ingredient, which only showed up a little bit before. And that's the notion of an integer partition, or really a decorated integer partition. So an integer partition of M is denoted like this by combinatorists, is a function lambda from n greater than 0 to n such that the sum over natural numbers of lambda sub I times I is m. So this is what I mean by an integer partition today. So that says lambda sub I, which is the value of lambda on I, is counting the number of times I occurs in the integer partition of m. So normally you think about an integer partition as just like, well, a bunch of numbers that add up to the thing. But what this way of encoding the integer partition is doing is telling us how many times I occurs. Lambda sub I is how many times I occurs in the sum. Does that make sense? Yes. Lambda sub I is lambda of I. Yes. Yes. One of these situations where the notation becomes unbearable if we don't subscript, I think. So further, I need a generalization of this. An integer partition of m decorated, and I could put any set here, but I'm going to choose a very particular one by G mod conj, is a function lambda from n greater than 0 times G mod conj to n, such that if I sum over all pairs of elements in the source of lambda, the value of lambda on the pair times I get m. So the way to think about this one, written lambda sub I. I don't know, is this a joke?
Is this, does
Oh,
it say such that the sum over I of lambda I?
lambda sub I times I.
Okay.
Lambda sub I times I is
Okay,
what's
thanks.
there. And this one is lambda sub I, comma, the conjugacy class of little g times I. Um, and here the idea is I have some sum of numbers equals m, but each of those numbers is allowed to be decorated or labeled by an element in G mod conj. And so what lambda sub I comma g is counting is how many times I occurs decorated by the conjugacy class of little g. Does that make sense? So why the heck is this happening? You may be wondering that. Well, you chose to be here. Yeah, why is this happening? So the reason this is happening is the following. So there's a canonical bijection between the conjugacy classes in G sigma m and the set of partitions of m decorated by G mod conj. So this is set of partitions of m decorated by G mod conj. And this is really useful because it's annoying to think about conjugacy classes in G sigma m. That data is just much more compactly expressed as one of these decorated partitions. You'll see how this is useful in just a second. But first, let me just say a word. I think I'm going to get to where I want to get to. Let me just say a word about what's going on here. So why on earth would you have a bijection like this? The point is that if I have the long cycle in sigma m, and then I take the element G1 through Gm sigma in G sigma m, It turns out you can conjugate this to be of the form gm times gm minus 1 all the way down to g1, comma, all trivial elements, comma, sigma. So it turns out you can just always conjugate an element of this form in g raised sigma m to be of this form. And so what I've extracted is a number, which is m, and an element in G, which is Gm to G1. That element is actually only well defined up to conjugacy, but that's why we get an integer partition decorated by conjugacy classes in G. So that's the idea of what's going on in this bijection. It is a fun exercise to try and figure out what element conjugates the left-hand side to the right-hand side. I suggest starting with m equals 2. Okay, so why are we doing this? Again, well, the point is the following. I said I wanted to understand the relationship between the power operation and the character map. And what does that mean? Well, ideally, what it would mean is that I take the power operation. This lands in Ru of G wreath sigma m. And I take the character map. And I take the character map. And what I'd like is some kind of map in here that makes this commute. It's not completely formal that such a thing exists. PM is just some multiplicative map. It's not additive. I can't just tensor with Q. But it turns out that this is a solvable problem. And the answer is that the formula down here, let's call this PMCL, that PMCL applied to some class function f, well, I need to evaluate it on a conjugacy class in G wreath sigma m. But that is the same data as one of these decorated partitions. I'll call it lambda. But these decorated partitions are just much easier data to work with than a conjugacy class in G raised sigma m, and the formula is very easy to express in terms of them. It's the product over I, comma G of f evaluated at G to the lambda I, comma G. And that's it. So I'm using that notation of decorated partitions, but this is yeah. So this is a formula that you can write down, and you can prove that this diagram commutes with this formula. In fact, I have a very slick proof that I'd love to share, but I think that that would be not a good choice given the amount of time that I have left. Does it make sense? The diagram commutes as even does the diagram commute as monoids? I want to make sure everything. I think the answer is yes. I think the answer is yes if we say that multiplicatively. Yeah. Okay. I have a goal. I'm going to try and get to the goal. So I want to talk about symmetric powers and Adams operations from power operations. Let me draw a diagram. Let's start with a big diagram, okay? This is going to explain how everything is related. I forgot to say a thing though before. Darn it. Okay, so let me say this thing that I forgot to say. Um, Here's what I forgot. So I forgot to say that RU of sigma m mod IM, this is the case that G is trivial, this is this transfer ideal, is isomorphic to Z. This is a fundamental fact, and I don't know what the most beautiful proof of this fact is. I know a proof, and I'm not too happy with it. Um, and the quotient map from RU of sigma m to RU of sigma m mod IM, and then follow it with this isomorphism to Z, this quotient map right here. This is actually the character of the representation evaluated on the conjugacy class of the long cycle. So I'll use a subscript for that. Chi sub the conjugacy class of the long cycle. That map from RU of sigma m to Z is the character evaluated at the conjugacy class of the long cycle. Okay. Hopefully that makes sense. Here's the big diagram. So big diagram. So I'm going to start with RU of G. I'm going to take the mth power operation. This brings us to RU of G reth sigma m. And I'm going to restrict along the diagonal map. So the diagonal map delta goes from G times sigma m to G reth sigma m. So it's including G into G to the m via the diagonal. This brings us to RU of G times sigma m. And once I'm here, there's two ways for me to get back to RU of G. One of them is to transfer along the projection. This brings me back to RU of G. When I do that, this composite right here, this is the mth symmetric power map. I'm taking, this is sending V to V tensor M mod sigma m, right? That transfer along the projection, the kernel of that is exactly sigma m. And we said that the transfer along this projection is quotienting out by the action of the kernel. On the other hand, I can remember that I've got this Knuth isomorphism. So this is this. And here, I can get back down to RU of G by taking the identity on the left side and tensoring that with chi, the character evaluated on the long cycle. And because of this discussion right here, we see that this map factors through modding out by the transfer ideal. In fact, that's exactly what it is. So the operation that I get through this composite right here is additive. And in fact, it's the mth atoms operation. That's what we get. So this is and it's a ring map. So it's both multiplicative and additive. Okay, so that's the big diagram. The fun thing is that we can give formulas on the level of class functions for everything going on in here at this stage, because we have formulas for PM, and we have formulas for restriction, and we have formulas for transfer. We know we have formulas for everything. So at this stage, we just have formulas for everything. And I'm going to tell you what they are. I have limited time, so we'll see. We'll see. Yeah, sadly, I would like to go through them a little bit more. Formulas for everything. So let's start with the formula for the restriction along delta of PM. So if I evaluate this on some class function f, so this is f is in CL of G, taking values in Q adjoin mu infinity, then I need to evaluate the resulting thing. It's in here. So in class functions on G times sigma m, and a class function in G times sigma m is a conjugacy class in G and an integer partition of m. And so the formula for this should be in terms of this data. And this requires some unwrapping of what's going on in restriction along the diagonal. But the resulting formula is that this is the product over I of f of g to the I to the tau sub I. And if you spend a moment thinking about this, you're going to think, whoa, where'd that g to the I come from? And the answer is the little g went into g raised sigma m by being spread across the diagonal. And the way we identified a conjugacy class in G raised sigma m with a decorated partition was by mushing all of the things of the same cycle type, but putting things of the no, out of the same cycle type, putting the g's in coordinates which correspond to a cycle all together, bring them all to one side, which if I have a bunch of g's there, exactly raises them to a power. And so that's where that g to the I comes from. Psi m is given by evaluating on the long cycle. So psi m of f of g, well, now I'm taking little g and I'm moving it into here by putting in the partition m partitions m, because that's the thing that corresponds to the long cycle, m partitions m. And so from this formula, the formula above, we learn that the value here is f of g to the m, which is what this specializes to, which is what this formula specializes to in the case that we just have the partition m partitions m, which is the case tau sub m equals 1. And then what about beta? So beta m of f, well, this one's got to be uglier because we have this transfer in the definition of beta. And so you just got to use the formula for the transfer along the surjection, which is I divide by the order of the kernel, which is m factorial. And then what I'm going to do is sum. I want to sum over the fiber of little g in g times sigma m. But I'm going to do it by summing over conjugacy classes, which is exactly what I said I wasn't going to do. So I have to keep track of the sizes of the conjugacy classes. What's the size of the conjugacy class of the element in the symmetric group associated to the partition tau? Well, it turns out that it's m factorial divided by the product over I of I to the tau I times, I see I have some notation in here that is illegal, times tau I factorial. There we go, like this, times the product over I of f of g to the I to the tau I. So this bit is coming from these restricted power operations, and this bit is coming from sizes of conjugacy classes. But things simplify here, actually. So a little bit. So this is the same as the sum over the integer partitions of m times 1 over the product over I of tau I factorial times the product over I. Maybe I could have just, well, that's fine. Of f of g to the I divided by I to the tau I. Okay. This is what you get. And using this, let me just conclude by saying, finally, using these formulas, you can check the sum over m greater than or equal to 0 of beta m t to the m is exp of the sum over k greater than 0 of psi k divided by k times t to the k. This is a check you can just do on the level of these formulas right here, and you'll win a relation like this for any representation, any G representation. But there is one thing to note here that is an important thing to note, which is that there's a dividing by k on the right-hand side. And as homotopy theorists, particularly, this should concern us because it looks like the place that this lives is in Q tensor RU of G, double brackets T. And it does live there. That's true. It does live there. But there is something more refined that you can say. In fact, it lives in a kind of divided power series algebra. So I don't have time to say what this is. I really wanted to do that, but I apologize. You can ask in questions what this is. But it, in fact, lives here, which is a somewhat more integral ring than the thing above. In fact, lives here, and this is a subring of the thing above, a proper subring. Okay, I'll end there. Thank you.
All right, let's thank Nat for the second lecture.